Hey, Jesse, I had the music still playing in the background. Good to see you here. What questions do we have? We can get started here on some review. Got a lot going on. It's a weird arm. Twitching my arm. Did my yoga this morning, got my coffee. Mewbot's here in the chat. Oh, let me re-awake Mewbot. Wake Mewbot back up. Canvas content number 9. Let's do it. Okay. Canvas content number 9. Hypothesis testing. We've done so much. We only really have one more chapter of content. So if you, as you have, been coming to all classes, if you've been doing that, just talking out to the world, if you've come to all the classes, then you know everything almost. You're only one class away, or it'll be next class, or not next class, it'll be next week, because that will be chi-squared. And when is this one due right here? I just saw it. It is due on the 1st, so next week. Good stuff. Let's do hypothesis testing. It's a really good thing to practice. I'm gonna close down all of these. We save these. I need to reset the internet today. Resetting the internet can cause a lot of issues, so we hope when we do it, it doesn't cause issues. Okay. 2, 4 to 3, stat 201. Canvas. Number 9. Let's do this. Here we go. Okay, we're going to do 2 versions of this and make sure we understand what we're doing. That's kind of the key to doing the Canvas contents, is to know what we are doing and why. So the first question right here says, a new diet is being tested. The inventor claims people lose 10 pounds on average after 6 weeks. 25 people are randomly picked to try the diet. A researcher concerned about the inventor's claim is that it's exaggerated. Researchers are concerned the inventor's claim is exaggerated. Good. The sample yields an average of 6.2 with a standard deviation of 6.1. Calculate the appropriate test statistic to 2 decimals. So here's the thing. This question's not bad, but you have to know what you're solving. So I'll solve it right here, but I want you to think about what we need to do to solve this. I'm going to solve it, and then I want you to think about the steps, because I want to show you how I would look at this problem if I have all the numbers. So I'd go 10. Oh, wait a minute. 6.2 minus 10. There we go. 6.1. What was that number? 3.8. 6.1 divided by 5. There's that. There we go. 3.8. This divided by this. There we go. But what do you think I know in the background while I'm doing this? What do you think I know in the background while doing this? What is the important thing to know that we're then going to solve together right here in a second that allowed me to get this answer, which should be the answer, I believe. But what do I know and I can look at? I think I did everything right. I need to double check my work too. Making a lot of errors lately. What do you have to know to get this question right? What do you have to know to get this question right? I think I've seen this one on the, maybe something to watch. There we go.
Notation, brother.
You got to know your notation. So the notation's the key to this problem, and it's going to tell us which things we are testing. So when we do this, we got all the TN voice right there. TN voice bonus for stat 201. We'll talk about some bonus for 322. So what is any of the notation here, Jesse? And this will actually help us solve it because we'll probably be able to figure out the formula. When it says test statistic, a test statistic means something like a z, a t, a chi-squared. So a z, a t, or a chi-squared, which we haven't gotten to yet. A test statistic is a standardized difference. Now we're not doing a confidence roll here. Boom, n equals 25. And if you get one more thing, you'll probably be able to figure out the rest, like what formula we're using. Because you can go to the formula page and look for what you're looking for and be like, okay, I need something that solves to a z, t, or chi-squared, so I'm doing a test. That'll lead to a test statistic. There we go. So with that, that means this is y bar, because that's the sample mean. Notice how these are sample average and standard deviation. So here's the big thing, Jesse. What is that? That's where people usually get stuck. That value is where people get stuck. And great job, you're getting them all right. So what is that value right there? That is where people get stuck on this. The inventor claims you'll lose 10 pounds. So I could write down the formula too. I'll start writing the formula and see if you get it. So it is T with n minus 1 degrees of freedom equals to y bar. I left something out right there. That value is mu naught. That is the claimed truth. So mu naught is whatever we hypothesize is true. It goes with the null hypothesis. So the null hypothesis for this would be that they claim, according to it, mu naught, great job, Jesse, right there. They claim the truth is that you will lose whatever that value is. So mu naught is what goes right here. The truth is this, and we are seeing if there is evidence that you lose less than 10 pounds. So we are investigating the claim, or we're trying to show evidence. So they believe currently you'll lose 10 pounds. We're trying to show evidence you'll lose less than 10 pounds because we're trying to show evidence it's exaggerated. Now, the question doesn't go into all this detail for later parts of it, but this is what you would be doing and using the t-statistic, and the p-value is going to be like 0.0001 or something very small if we do find it. So all we have to do now is just plug in the numbers. So we plug in right here the sample mean. I'm going to delete that. The sample mean is 6.2 minus 10. That top part is just a difference right here. And then the bottom part is how we standardize it. So the bottom part down here is the standardization of s over square root of n. So that's 6.1 over square root of 25. And tell me it is. So Jesse's confirming negative 3.11 right there to 4 decimals. And then what I like to do is, and there it is right there. Great job, Jesse. Excellent work. So since I knew the formula, I was just kind of working through it in my head. And that's a t with 24 degrees of freedom. Degrees of freedom equals n minus 1 equals 24, because sample size is 25. And here's the thing, Jesse. The p-value is going to be very, very what? You can go to the applet and find the p-value for this, which we're just doing like additional things to understand how to work the questions. But we landed right here, and we're graphing to the left of it because we're doing the less than alternative. So this is where the t-statistic is at on a t with 24 degrees of freedom. Very small, right? So that's why when I said it's going to be something like 0.00, I'm going to go 2. There we go. So I'm going to go 0.002. That's my guess for it. Because think about when you do 68, 95, 99.7, 0.0015 will be on the outside, but this is a little further over than 3 standard deviations. So it's going to be very, oh, that was me. Jesse wrote small. I thought Jesse, I was like, oh, thank you so much. So T with 24 degrees, still great job, Jesse. Find the p-value below 24 degrees of freedom, t-statistic, and 3 decimals.
Wow.
There you go. And that's how we can sometimes figure out the p-value without even using the applet. And we had a good indication right here. And if you take a look at the picture we have, this picture right here, which shows the p-value, we were able to take a pretty good guess at it. Can I get it on the screen at the same time? Here, we'll put it over here to the side. So there's my drawing, and then there's the applet. And the applet, I'll disappear off the screen, looks pretty similar. It's very hard to see maybe on the applet, but it's this area right there because that's where we landed at negative 3.11. And then the shaded area is the p-value, which is equal to that right there. A result as extreme or more extreme. And we were able to guess the p-value. So this would be reject the null at any reasonable alpha level. We have evidence of a difference, or we have evidence that they are not meeting the claim that they're exaggerating it. So all they wanted was the t-statistic, but we actually did the false hypothesis test and rejected the null. Entered to 2 decimals, make sure to round. So this is the same thing. A new diet is being tested. Researchers are concerned the claim is exaggerated. So when we do this, can you do mine? Yeah, y bar, 8.9, standard deviation 7.5. So that's a difference of negative. Okay, so let's first find the standard error. The standard error is going to be 7.5 divided by 5, right? So that's the standard error. And then, yep. Because your difference is a lot smaller. Good answers, Jesse. And there you go. Yep. Great job, Jesse. Good work. And I'm more than happy to check those. And think about your difference is a lot smaller. So your p-value is going to be a lot bigger. If you were to check it over here, your p-value is probably going to be like, which it doesn't ask, don't put in the p-value. Your p-value is probably going to be like 0.262. It's much harder to guess the ones towards the middle of the curves. I said 0.26. Yeah, no, yeah. Well, think about it. In your example, they lost 8.9 pounds, and in my example, they lost less. So think about this. My difference is water here than your difference. The difference I observed was water than your difference, where you had 8.9. So the difference I had was water. I think our standard deviations are similar, bigger. And actually, your standard deviation is bigger. So there was more, you had more variation with a smaller difference, right? Which is going to lead to a much smaller t statistic. So just theoretically, because the variation in your data was more, we had the same sample sizes, your difference was smaller. So your difference is a smaller standardized difference than my difference. And that's what's really great about this is both of our differences are equally compared by doing t statistics. The t statistic is always the same. It's how many standard errors is it away from the hypothesized value. So Jesse, great job and good questions right there. Like, why is this different? Well, you had a smaller difference and a larger variation in your data. We can narrow this down to two choices pretty quickly, given we can do it, which we can do it for this problem. The only two reasonable choices on the screen are what? This makes it an A or B choice. Well, the only two reasonable, the one or two, right? The first two. The null has the equal sign is a giveaway right there. If you're worried that a diet is exaggerating their claims, the null has the equal sign. Boom, right there, we got that. So now you're worried, you're trying to show evidence the claims are exaggerated. So if someone's like, dude, you need to try this diet, like you can lose 50 pounds in a month. Don't do that. So if you were to say the claims are exaggerated, you'd want to show evidence what? You're saying you think the truth is less than what they're claiming. So there we go right there. We got it. No text provided. These are the answers, obviously. Don't click those. A small p-value provides strong evidence against the null hypothesis. I feel like we took this straight from MyPearson, so don't overthink this. It's not like the MyPearson questions where we're trying to be too crazy on the wording. I mean, you never say things like prove. So if you see prove or cause in any problems, those are false. But when we talk about evidence, we want to say there's evidence for the alternative, and that'd be evidence against the null hypothesis. So once again, I don't think we get too crazy on our wording because MyPearson really gets to some exact stuff. Like if you look, like we don't have like 3 other true statements or something here, but a small p-value is evidence to reject the null, i.e. evidence against the null. We do say we have evidence for the alternative, but there's evidence to reject the null, I would say. But yeah, I don't know. We could get very, very exact. That's how we statisticians are. I love how I predicted the next question. What do you think? Question 4, Jesse, what do you think? This one, I mentioned this a ton in class. Hopefully someone gets this question is like, boom, just knows the answer. So there's some tricks to this question which can make it very easy. Jesse, thank you for saying that. 1,000 points, Jesse. This one is false because 1,000 points are there. Hey, Jamarcus, good to see you here. This one is false because we never say things like prove or cause in statistics. So we don't use the words prove. We don't use the words cause in statistics because, so this is false. So good work right there. Good practice. Let's take a look at this example right here. We've got weight explaining someone's height. So it's actually male and female data right there. So there is a statistically significant relationship between weight and height. This goes back to regression. So does gaining weight cause people to get taller? Now you might say, well, when you gain weight, you generally get taller. But think about this. Does gaining weight, it doesn't cause you, right? So even like with regression, a small p-value here is evidence of a statistically significant relationship. What a small p-value shows us is that the relationship between weight and height is what by what. The relationship we see between weight and height right here is what by what. And that's a key phrase to know. Like the relationship we see where people who weigh more are generally taller is a relationship that is what by what, i.e. low p-value, i.e. statistically significant. It means that this sort of pattern in this data would be what by what. The pattern we see in the data Low p-value means what? I was going to go right here to think what statistically significant means. Statistically significant means unlike. So it doesn't mean, and good answers right there. Not that it's not by random chance. It's unlikely by random chance. So what I'm going to show you right here is what is likely by random chance. So this right here is me completely randomizing. Yep, unlikely. And that's the lower the p-value, the less likely it is by random chance. So we can get really low p-values that say what we're seeing is not likely by random chance. So here is the relationship between height and weight. I think it's the same data. So here is the relationship between height and weight right here. There's the relationship. And you can see a line would go through the data going up. And let's do this right here, or one last thing. Well, so with this, well, actually, it's going to be easier if I do this. M, save into LM, and then height tilde weight, comma, data equals survey 10. And then visualize model. There we go. There's the relationship between height and weight. Now watch this. Here is what it would look like by random chance. We're just going to take the same thing right here and go M, save into LM, Y tilde X, and those are the variables, and then visualize model and run it all. Visualize model M. And now here's what it looks like by random chance. By random chance, the line would be very flat. So these are all random chance models right here. Oh, I didn't remake the model. That's why. So these are all random chance models. And look at how flat they are. Now compare this to our original model way back in the day where we had a model that wasn't flat. If we go all the way back here in time to the first model, it has a much stronger statistically significant relationship that is unlikely by random chance. Here's the not by random chance model. And here's all the random chance models here that are likely by random chance. The slope is close to 0, and we would see right here if we go to the summary on it that it is not statistically significant. I got lucky. We could have had a type 1 error, and that's the next question coming up, where you reject the null and the null is true. Definitely a lot flatter. Yep. And you see how it's not statistically significant? So the relationship between height and weight right here, pretend it's height and weight or whatever x and y is, the relationship between x and y is likely by random chance, where opposed to the previous one, the relationship between height and weight is unlikely by random chance. So this one right here had a statistically significant p-value telling us that the relationship between height and weight is unlikely by random chance. And that was this graphic right here. Same graphic, same data. P-value is low. Statistically significant relationship. Height and weight have a relationship that is unlikely by random chance. That is what we mean when we say low p-value. When we reject the null and the null is true, we've made a what? Very easy. We practice this a lot. When we reject the null and the null is true, we've made a what? This one should be pretty easy right here. So when the null is true and we've rejected it, type 1 error. And that's why I love teaching it that way. You get to these questions on the test, boom, you get those questions right. Let's do another version of this. Really good practice right here to understand these and to know the concepts behind them. 10 out of 10. So we'll do the ones quickly that we've already done. So this one right here we've already done. We're seeing if there's evidence the claim is exaggerated. We did this one. We'll take the difference. Well, first off, let's find the standard error. The standard error is that. The difference is 3.4 minus 10 divided by the standard error. There's the test statistic. I think I did it right. A type 2 error. So they kind of say it. Well, no, this is perfect. Once again, I come up with ways of teaching these things. Yep, we did the diet one earlier. Check it out, or I can go back over it. We went over a full explanation of how to solve the diet one with additional solves and marking the questions. But marking all the notation right here was one of the first questions we did. Let me know if you're stuck on it. And then we can speed solve it if we know the notation. So in a type 2 error, just tell me the first letter I make right here, which is key to knowing this. In a type 2 error, what letter is that? Because then you can pretty much solve this. Like if you know this right here, F, right? So here it is right here is the answer, and let's point out why. In a type 2 error, the null is false and we fail to reject it. There are two F's in that saying. There's two F's in the type 2 error. In a type 2 error, the null is false and we fail to reject it. There's the second F. So thank you to Hannah, who made this up years ago. Gosh, like 8-9 years ago. She was like, wait, hey, Brian, check it out. In type 1 error, the null is true and we reject it. In a type 2 error, the null is false and we fail to reject it. I don't know. She came up with it. She doesn't do the, we've advanced it, but she was the one who came up with that originally. And I was like, that is genius. We're using it. And I've had so many students remember it. It's a lot easier than a lot of the graphics you see where you basically just have to memorize it anyways. But that saying right there has helped, I think, tons of students. I've even had other educators use it. So once again, shout outs to Hannah right there. If you think of something really great, maybe there's a great way to remember things, and that'll help future students also remember these concepts. What does it mean when the null is false and we fail to reject it? Well, we do a lot of examples with this where, do we have any examples? I think we were doing type 1, type 2 error yesterday some. There it is. So we were doing one where they might have revoked the inspection of a brake place to see if they're properly inspecting the brakes. So in a type 2 error, the null is false. So it's false that they're doing good inspections. It is true that they're doing bad inspections. So it's true that they should revoke their license. Like, the truth is that this brake company doing inspections should have their license revoked. But we are going to fail to reject the null. So usually if you write this out and do the drawings like I do, I always try to draw it. I'm trying to think. It's that, and helps me. It's that it is false that they're doing good inspections. The null is false. We are not going to reject that, though, and believe they are doing good inspections. But the truth is that they are doing bad inspections and we should revoke their license. So kind of walking through like that, like pointing to the null and be like, that is false. It is false that they're doing good inspections. They're actually doing bad inspections. That's the truth. But we are going to fail to reject the null. Just some practice with that. It's easy to make mistakes. Fun story. It was one of the first problems I got wrong with students. And students went to Charlie, the coordinator, and they were like, Brian told us it was this and he reversed it. And I probably did. It's easy to reverse. Smaller p-values provide stronger evidence against the null hypothesis. True. The lower the p-value, the less likely our result is by random chance. Low p-values prove a cause and effect relationship. I threw prove in there to make it even falser, but that is false. Let's do one more version of this. What do you think, Jesse? Is it a little bit easier now? And remember, we're just trying to remember how to do these and understand the concepts behind them. Hey, Arista, good to see you here. Ask any questions you got. Awesome. We'll do one more version of this. This is the diet question. Once again, I'm going to find the standard error, which is s over the square root of n. So s over square root of n is 6.7 divided by square root of 25. There we go. Find the difference. This is a rather big difference now. There's the difference divided by the standard error, and there is the test statistic. If you know your notation, not a bad problem. The diet's claim, we want to see it's less than what they're saying. Small p-values provide evidence against the null. Very true. When we reject the null is true. Reject the null is true. Type 1 error. And type 2 error is when the null is false and we fail to reject it. Well, I'll be. Look at it. We're just speed running this quiz now. Try it one more time. We didn't get anything new. Trying to get something new here. There's the diet question again. And the diet question is, we're going to take 6.9, which is the standard deviation, divided by 5, which is square root of 25. Did you get, yes, I think so. I think it came this morning, right? I think you emailed me this morning. And I will be replying to it. I think I saw it, and I was replying to emails from last night. Thank you, Jamarcus. Yeah, definitely. I think it's, well, and then last thing. And the small p-value provides evidence against the null. When we reject the null is true. Type 1. Low p-values are evidence of cause effect. Well, I think that's it. You want to get to where, if you're watching this right now, basically, being able to explain is the key, not just knowing the answer, because you don't want to just memorize these questions. Like, the null always has the equal sign. That's how we narrow this down. And they want to see if it's exaggerated. So that would mean they don't think you're losing as much weight. So we want to see if there's evidence that the true mean of weight loss is less than 10 pounds. Right here, we're going to take the standard deviation and turn it into the standard error by dividing by the square root of n. Sets the quantity of the standard error. We're going to take the difference of 4.2, which is what we saw in the sample, subtract the claimed amount, and divide by the standard error to turn it into a standardized test statistic. Next, type 2 error. In a type 2 error, the null is false and we fail to reject it. And low p-values are evidence of cause and effect. We never say cause and effect are proven statistics unless we're doing design of experiment, which we don't teach in this class. That can be good evidence of a cause and effect, but that's different class, different day. When we reject the null and the null is true, when the null is true and we reject it, that's a type 1 error. We don't have type 3 and 4 as far as I know. Never talk about those. But that's got it. We just did like 5 or 6 versions of this. Good work. What other questions are there? What questions are there? Love it if my contact was good again. What questions are there? Data Analytics 7? Yeah, we have a video on it. Yeah, we did pretty much all of it. So Arissa, yeah, let me pull up the video right here and we'll do a short talk about it, and let me link the video in the chat. So let me get Data Analytics 7. And I'm going to talk a little bit about it. So this is like, let's call this like a high level Data Analytics 7. I always like to do things like differently each time. So we do something again, I like do it a bit differently. And then we get different ways of doing it. Oh, Jesse, you are on fire. Jesse's already got it. Holy mackerel. Thank you, Jesse, right there. So here is the Data Analytics 7 right here. We're going to pin Jesse's comment right there. Thank you so much, Jesse. Let's start at 1,000 points. You are faster than me at this. Here it is right here. It's timestamped with the portions we're working on it on. And so we'll talk about these things too. So let's talk about confidence intervals and hypothesis test and interpreting results. So this is kind of be a new spin. Let me mark this in the video. And I want to do it more as a teaching style right here and a quick review of it, which will lead into the ones you're asking about. Sometimes how fast. Yeah. When do we know info about our report? I think Terry's putting it out in the next few days. Shout outs to Terry. Working super hard on that. Already got the exam stuff posted, but we'll have that posted real soon here. Thank you, Terry Higgins. Awesome job. Stat 201, Data Analytics 7. So if you're watching this, I highly suggest going to the video. I'm going to talk kind of about confidence intervals and about tests in JMP. So check out the part of the video right here. But here's what we need to understand. When we do confidence intervals in JMP, so I've got a data set right here with confidence intervals with where I can do tests. What do you notice about gender and height, and what is JMP telling you right here with handedness and these other variables? So that's the first thing to notice about doing data analytics. So I hope you'll use this after the class. Like you might be in a class where they say, hey, we need to do visualizations of data. And you might say, hey, I know how to use JMP. And they'll be like, oh, cool. I took Stats 1 also, and I forgot how to use it. It makes doing data pretty easy using JMP. So I'm hoping you get to use this in other classes. What does that blue and red thing mean over there? Actually, if you click it, you can get some additional advice on it. Kind of says ordinal, nominal, or none. Won't let me do continuous there. So what's this whole continuous thing? It says continuous, ordinal, nominal, none. That is the type of variable we're working with. So ordinal and nominal are both categorical. Ordinal means it goes in an order. It'll change it to like a bars that are in order right there. Nominal means it has no order, which handedness doesn't really have an order to it. Like freshman, sophomore, junior, senior is an ordinal categorical variable, but handedness, left, right, ambidextrous is not ordinal. What's really great is you can click one of the variables and then you can go over to analyze distribution. And so analyze distribution analyzes one variable at a time for you. And we're just going to click that right here, then double click handedness and click OK. Now, this is going to be a categorical variable I'm analyzing, so we get to see the proportions of people who have a certain handedness. So this can be used to do your Data Analytics 7, kind of letting you know what the output looks like. We're going to go here to stack. Boop. And then I always like to make this a little bit bigger. Then I go here to the second red arrow, histogram options, count access. Histogram options, count access. That shows you the counts of individuals in each bin. Oh no, did Terry ask us to put the... Did I not put the show counts? I so rarely show counts over the bars, and did he say to do that? Did he say to show counts? I feel like he usually puts in show counts, and I didn't do that. Did he say show counts? Show counts are percentages over the bars. don't like people losing points. It's just a preference thing. Knew it. How much is that going to lose people? Where's the screenshot portion? Correct screenshot. They shouldn't. It might cost someone 0.25 points. Still not happy about that. With the count axis, it's usually enough, but for this one, he wants the counts shown over the bars, and that could lose someone 0.25 points on that. It does say it in the rubric, doesn't it? Does it say it down here? Analysis of yeah. Jack, good to see you here. Well. Yeah, we don't put counts over these bars usually. Ugh. I was so concerned about changing my histogram color. Like, I can literally watch the video in my head right now. And so make sure to include that. I probably need to email. I'm going to email my students really quick. So please. Might mention in class tomorrow too. Announcements. Data Analytics 7. Counts over bars. For the first graphic, make sure to include counts over the bars. I didn't do this. My example on. Let me send the video too. Video help. We'll send the video help to people. That'll be good. And there we go. Got that. Send this. And we got it. Okay. Well, man. Should have an announcement now. Yay! So when you're doing this right here, the major important part of it is understanding confidence intervals and knowing how to interpret confidence intervals. Because with confidence intervals, you want to go here to confidence interval and insert the right percentage that you're doing. So a lot of times we do 95% confidence intervals. You can click other and enter in any other percent you want. And so here you are right here with your 95% confidence intervals. But here's where people lose points on the test. So many people, I see it all the time, do not know how to interpret the confidence interval and know what it means. And that's the whole point of why we're doing this. So I'm going to throw 1,000 points if anyone can interpret the confidence interval for right-handed. So if you're in the chat right now, if you're watching this video in the future and you want practice for the test, how do you interpret the confidence interval for right-handed? And we're talking about Stat 1 students. So how do we interpret the confidence interval for right-handed? And then, Jesse, if you want to put some Chapter 16 quizzes in here, people usually don't remember how to interpret these intervals. You have to think, what are you analyzing? And then you have to think, does it make sense? Mine didn't include it. Over? What did yours not include? Over? What? How would we interpret this confidence interval? So the confidence interval interpretation is, write down right here while people are thinking over. I am blank % confident that the true blank is contained in the interval blank to blank. So I'm going to label this part of the video interpreting confidence intervals because this is what we need to practice. A lot of people can't do this on the test, and this is worth a lot of points. So Stat Tool 1, interpreting confidence interval. Practice. Okay, so if you're at this part of the video, you should be able to write this down. Oh, good job, Jesse, right there. Good practice. So the confidence level is 95 right here. So that would be the confidence level. And this is actually, circle it. Throw you those 1,000 points. Yep. But not mean. Good answers. Really good practice. The rest of you can get those points too. So, this is E hat. This is the lower. This is the upper. This is the percent confidence. And that's actually X, and that's N. So to mark our stuff right there. Oh yeah, so whatever you want to use, Marcus, let me know. I think Arista has it. I am 95% confident the true percent of people who are right-handed is contained in the interval. Exactly. And then you could make it percentage. Great job right there, Jesse, and great work, Arista. And we'll throw those 1,000 points really quick before Jesse leaves. That is correct, Arista right there. We'll make it 2,000. Thank you, Arista, for commenting on that and throwing in your interpretation. And so the big thing is a lot of times people put means, proportions, or forget to do the difference between means when we're interpreting intervals. We'll either say mean here, proportion, or difference in means. Then we have to give the context. So a lot of times people get stuck on this because they say, well, wait a minute, how do I interpret this? What do I need to say? And we would say, I am 95% confident, that's 1 minus alpha level of confidence, that the true proportion of people who are right-handed, and you could say percent, that also works, but then I would change the last two numbers to percents also, is contained in the interval, the lower to the upper. So we'll mark this right here. Lower to upper goes right here. The percent confidence is going right here. And we are doing proportions because it is categorical data, like the proportion of people are right-handed. So now think about this. I might interpret this one, then we'll do a little chapter 16. Because we're gonna do the whole homework tomorrow, I believe. Is that, or did we do 16 last week? We go here and analyze. Oh, that's your data set. And so let's go back to a different data set right here. Let's go to analyze. Oh my gosh, we're just gonna go straight to 1 billion ones of those data sets. Let's go here and do analyze distribution. And let's go here and go to GPA. And when we interpret this, you'll notice GPA is quantitative. So you get this sort of interval right here. And you could be asked to interpret this. Let's go interpret it. So how would we interpret this right here? So Jamarcus and Arista, how would we interpret this interval right here? We'll bring it back up on the screen with it. We'll do the last interval interpretation too. So if you're watching this part of the video in the future, you can use it to interpret intervals and to understand what you're seeing and how the output looks different. So where are the parts we need on this? Once again, really good practice right here. Get ready for the test to know how to do these things. I'll mark the notation while you do it. This is Y bar. That's the sample mean. This is the sample standard deviation. This is the standard error of Y bar. This is the lower of the interval. This is the upper of the interval. This is the sample size and degrees of freedom it didn't give, but degrees of freedom are 698 and minus 1. The standard error can be used in formulas like Y bar plus or minus the T star with n minus 1 degrees of freedom. Then the standard error goes right here, which is S over square root of n. So we could do a confidence interval with that. We can also do a t-test if we want, which is going to be t, no star, n minus 1 degrees of freedom. And then y bar equals mu naught. We'd have to test a value and then do s over square root of n. It is important to note that this value right here, the standard error, is this, which is also this. So those are interchangeable, writing the standard error. So knowing your notation and what formulas you might use for this problem is very important. You can see the n minus 1 degrees of freedom, which goes with the t right there. I am 95% confident that the true mean student GPA is... Arista, you got this down. And then we're going to do one more. And I might even interpret the last one for you. Arista, 1,000 points. That's exactly it. Arista notices right here the percent confidence is going to be 90. I didn't even mark that. There's the 95% confidence, which goes up there. I am 95% confident the true mean GPA, because this is all quantitative, because we see mean right there. That's a huge tip right there. And then between the lower and the upper, and so the lower is right there and the upper is right. Ooh, Brian reversed his notation. And the Arista still wasn't tricked by that. Arista got it right. So here's the upper, and there's the lower of the interval. And it's best to go from low to upper. So, between like 10 to 20, 30 to 40, you don't usually say 40 to 30. So the last one right here, we're going to take our interpretation right here, and we're going to do one last one, and we'll have done all confidence intervals interpretations, because the only one we haven't done yet is the difference between means. So now when we do the difference between means, this is chapter 17, which we just did yesterday. We have to go back to the data, and we have to go to analyze, really. We have to go to analyze, fit y by x, and then we would look right here. And let's go to number of body piercing, and we'll do weight. Sure. So this is difference in weight between gender right here, and let's analyze it with the t-test. There we go. And take a look at how the formula's figured out. We've got it right here. Boop. And so how would this sound? And I'll mark the notation for you. Feel free to start thinking about what you're going to write as I mark all the notation on the screen. It is y bar 1 minus y bar 2 right there, the difference in the sample means. The standard error is the standard error of y bar 1 minus y bar 2. More specifically, the standard error, I have to write it down below here. The standard error of y bar 1 minus y bar 2 is equal to square root s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. And the lower and the upper of the interval are just the lower and the upper. So that's upper and that's lower. Confidence level. The t ratio, this t ratio is found by t equals to y bar 1 minus y bar 2 over the standard error of y bar 1 minus y bar 2, which interestingly enough is just literally this. That equation right there is literally that, because look over here. That's just the difference divided by the standard error. So you can just divide those numbers. Here, I'll show it. I try to help people remember this, because you can just divide 43 by 1, or there's the 43.1626 divided by 2.3138. The difference divided by standard error is the t statistic. The degrees of freedom is the complicated formula. It's too complicated, we like to say. Check out my other videos on how to calculate it using the applet. I'll show that really quickly because we're mentioning it here. If you want to calculate the degrees of freedom, you would need to go to the stat applets that we have. So we're going to bring up the applets to do the degrees of freedom. And it is a complicated formula. Also put the formula on the screen. 2 sample t degrees of freedom formula. And 2 seconds right here. So the formula we are solving is the following formula. We're solving this. If you notice, it takes standard deviation 1, standard deviation 2, sample size 1, sample size 2. So if we were to do this, we'd need to go over here to the t. On the t, you'd go down here to calculate Welch's degrees of freedom. If you notice, it has boxes for you to input the degrees of freedom. The sample sizes and the standard deviations. If we're to do all this work by hand right here, we would need to go to the data and go here to means and standard deviations. So the standard deviation for the first one is 25.1. And I think I saw 386. And then for the second one, this is like the long way, 34.13. And then sample size 313. And degrees of freedom 558.6. And I think it carries that over for you. It doesn't. That's that's the one change I would make right now. And if you look right here, 558.66. So maybe we didn't carry enough, but maybe if we carry second decimal, probably the way we calculated it, yeah, we might just need to carry more decimals on all this, because it's probably going to start to, yeah, look at that little change right there if we carried more decimals. Either which way, we have enough that our calculations are going to be pretty exact. Jump's just going to do a lot more work for us and carry more decimals on these numbers. And then we get the degrees of freedom right here, which tells us the shape of the t. The shape of the t, the lower the degrees of freedom, the less normal it is. It's more peaked and has wider tails. As we increase the degrees of freedom, it goes towards the normal curve, and famous numbers we know like 1.96 start to appear as you increase the degrees of freedom. So with few degrees of freedom, you see more drastic differences between the t and the z. With higher amounts of degrees of freedom, it converges towards 1.96 or 1.95996. That's what t actually is if you carry more decimals. And then there's even more decimals. Those are the p-values for each of the tests down below. So this is the less than test. This is the greater than test. Oh my gosh, what am I saying? This is the does not equals test. This is the greater than test. This is the less than test. And there are relationships those p-values have that we should know. But when we're interpreting this interval, we have to think about how we're interpreting it because we have an interval here. So I am 95% confident that the true difference, there's the confidence level. I am 95% confident that the true difference between the mean heights of males and females is contained in the interval 38.6 to 47.7, with males being taller than females. And the difference is because the difference is positive right here. So that's why we believe there's evidence, and Jesse's at that new level right there. There's evidence that males are taller than females. So we're doing amazing analytics right here with evidence males are taller than females. But does that mean being male causes someone to be taller? No. It's just evidence that there's a relationship between the two variables where typically males are taller, not taller, excuse me, way more. This is weight. We were going to do height, but this is weight right here. So I am 95% confident the true difference in weights between males and females is contained in the interval 38.6 to 47.7, where males are typically heavier than females. There we go. Rachel, good to see you here. Yep. We actually have it pinned as the top message right there, and we're doing some interpretations of the confidence intervals right now to practice doing each one of the interpretations to get ready for the test. So this is interpreting each interval. Oh, I guess we replaced the first one, or no, it went off the screen maybe. But we just did interpretations of each video, and then the pinned message right there. Do you see the pinned message at the top? That is at a timestamp going to the video. You're welcome, Rachel. Thank you for asking. And then check out this video right here to learn interpretations, and make sure to include, and I sent out also a link to all the classes with this video too. Oh, well, to classes I teach. Chapter 16. Well, maybe we should do some 17. I'm trying to think what's due right now. Let's figure that out. What is due right now? What is due? You're welcome, Rachel. Let's see what is due. Here it's Analytics 6 should be graded. I have 1 week to grade. I'm trying to keep up with my graders and be like, make sure. When was this due? Okay, good. It's supposed to be graded about now. Okay. Making sure we're on track as the semester comes to a close. Very important. Good to see Jackson right here. You're welcome, Marista. And great job practicing right there. Those are the three, that's everything confidence rolls for the class. We didn't mention the conditions, but the first one would have been random 10% success failure. The next one would have been random 10% nearly normal. And then the last one would have been random 10% nearly normal, and then independent means. Or independent groups, means groups, same thing. And so knowing the conditions, knowing all those things, excellent right there. I guess we have chapter 16 coming up here. And so, yeah, do a little chapter 16 homework. We'll end off with that. Chapter 16. We'll kind of do some teaching on this to show how to do it and what the concepts mean. So if you're watching this part of the video, then we will kind of explain the topics, which I love doing, because it's not about getting the answer to one question. It's about understanding how to solve the answers and what it means. So let's go to the chapter 16 homework and just do some parts of it and talk about the concepts within and what we need to know. Okay, let's do it. So these can be really tricky. These are really tricky questions. They're very exact. So what is a p-value? Well, first off, let's try to understand what a p-value is. A p-value is, and let's zoom in on this a little bit here, the probability of our results or results more extreme happening by random chance variation given the null is true. Now, this really doesn't help us understand what a p-value is. It's just kind of a stat book definition. And so let's think about it. Null hypothesis, which is an initial belief. We'll write that out right here. The initial belief we have is called a null hypothesis. We don't need evidence for this. We are looking to see if we should retain it, not reject, or reject it because what we saw was unlikely given the null is true, i.e. low p-value. Now, here's where I hope we can start to show some examples and think about how this applies when we do this. Because we might have someone with a null hypothesis. Your friend says to you, they say, I can run a 6-minute mile. Your friend says, I can run a 6-minute mile, 6-minute mile on average. You believe, you want to show evidence, I should say, your friend is slower than this. So in terms of writing it out right here, it's going to look the following way. It's going to look like this. The null hypothesis is your friend's average mile time is equal to 6 minutes. The alternative hypothesis is that your friend's average mile time, because it's quantitative, is greater than 6 minutes. Now, slower means they take more time than 6 minutes on average. So that's how we would write out right here if we were doing the notation on it. And this is what you would see. You'd go to the track, and then you'd watch your friend. Great job right there, Jackson. Good practice. And so you'd watch your friend go out here to the track on, let's say, 2 weeks. You take 2 weeks of data. They say, okay, I'm going to stretch right here. I'm going to do some stretches. They're stretching out, and then they do their mile time. They do a little, every time in track and cross country, we'd always do like a mile or two run. Like, okay, let's get ready. Let's run 2 miles to get ready to run a mile, or run a 5K. Let's run 2 miles. I was like, it's tiring me out. I'd love to do an analysis to like, what is the proper amount to run before a race? I don't know if anyone's ever done research on that. Surely someone has by this point, but I don't think there was that research when I was in doing it. I should have, man, if I knew what I knew now, I'd do an experiment and like have people do random amounts of running and maybe tell everyone this is the best amount of time. Or maybe tell them we're doing an experiment to see if that, like, do that variable. So here we go. This person's running around the track. And what you would get right here is when you run this, you'd get the Y observations. So the Y observations right here, this is why we call it Y bar, is all their different times when they run the mile, like 6.1, 6.2, 5.9. And that's what we call the mean of this data Y bar. So now we would have a Y bar right here, and Y bar is their average mile time of 6.2. But if you notice, they don't always run it the exact same amount of time. There would be variation, and the standard deviation is the metric of variation right here, which would be something like 0.5. So now you might say, well, they didn't run it in exactly 6 minutes, but they're saying I can run 6-minute miles on average. So you're saying, well, wait a minute, they are taking longer. So a lot of people would say, well, I didn't see my friend run it in 6 minutes, but I think if we did this, you might believe your friend, because now it's basically 6 minutes. But the question becomes in statistics, when is it basically 6 minutes? Now, I'm not saying 6.2 is basically 6 minutes, but we're saying in statistics that their claim might be believable with 6.2 minutes. You don't need to use statistics if you watch them run their miles in 10 minutes on average. At that point, you would know without statistics pretty much that, yeah, you can't run your miles in 6 minutes. I saw it taking you on average 10 minutes. So here we are in one of those worlds where we need statistics to think, is their claim believable? So what we would do is we'd run a t-test right here. Remember, they did it 14 times. I didn't list all 14 times, but we'd go here that the t-statistic with n-1 degrees of freedom is equal to what we saw in their sample minus the claimed amount, which is this right here. This is mu naught, their claimed mile time. And then we divide by the standard error the following way. So we saw 6.2, which is a difference of 0.2. We divide by the standard error, which is going to be this right here. This gives us a t-statistic of, I'll have the t in a moment right here. What is the standard error? Square root of 14 and 0.5 divided by this. Ooh, this is an interesting one. The t statistic, as far as I can tell, is 1.66. That's a close one. This is where you really do need statistics. 1.49. I was off. Yeah, I can do math in my head. We're going to round it to 1.50. And so that means when we do this, we saw something over here. And so what is the probability of this time? So we saw something here at 6.2. I'm going to write in purple. So the observed result is 6.2, given 6 is true. And what's the probability of something of 6.2 or higher? See, the probability of our result, 6.2, which is what we saw in the sample, or a result more extreme, because we're doing a greater than test, given 6 is true. And the p-value on this, because we're doing 14 different trials right here, so we got to go here back to the applet. And so let me go grab the apps right here. The p-value on this, t-applet, and 13, and we're going to go here to p-value, and we're going to go to above, and we're going to go to 1.5. Oops. 0.08. Wow. So here's the thing. It's a close call at this instance. Your friend's taking like 6 minutes and 12 seconds or so because it's about 6.2 mile. But at this point, and I want you to look at the graphic I have drawn and the graphic right here on the screen with the p-value. You always want to be able to draw kind of an instance of your graphic over there. So that's the graphic I drew, and this is the graphic they draw. If you notice where the line is at, it's at 1.5 on both graphics, and that is 1.5 standard errors, but that's where 6.2 is at on the graphic. So with this p-value right here, using the 0.05 standard, you would have to still believe your friend. I mean, it's on the edge of what's believable because the p-value is 0.078. So the p-value right here is 0.078, and you would fail to reject the null hypothesis. So you're saying, yeah, I guess I believe you. I mean, you did something kind of close to what I would expect to see. And so using that knowledge of what a p-value is, it's the probability of what we saw. A p-value of 0.01 means the null hypothesis is false. Well, it's about our results. So the p-value provides evidence against the null. Yeah, it doesn't show it's false. We say we have evidence against the null. The p-value provides evidence against the null depending on the alpha level. No, we don't say the null is false. We just say I don't believe the null anymore. The null could be true. Whether the null is true or false is not, it just is. That's a fact of the world. The null is not proven false. We do not know the null is false. We just have evidence to reject it. A p-value of 0.01 means the null hypothesis is a 0.01 chance of being true. This one got me on yesterday's assignment. It's the probability. Well, we don't really say the null is true. It's that our observed results. So the p-value is not the probability that the null is true. Yeah, exactly. So this is a slightly different version than last time. The p-value is not the probability that the null is true. It's the probability of our results. It's saying, is what we saw in our sample right here likely given the null is true? So it's not the probability the null is true. It's the probability of the observed result or a result more extreme given the null is true right there. So that is false right there. The p-value is not the probability the null is true. Good question right there. A p-value of 0.01 is evidence against the null hypothesis. I mean, pretty much. This is where whether a p-value provides evidence for the null depends on the alpha level. See, wait, this is evidence for the null. We don't have evidence for the null, so that's just false. We have evidence for the alternative, and we would probably say whether the p-value provides sufficient evidence for the alternative depends on the alpha level. The p-value provides evidence. The p-value provides evidence for the null. It does not. The p-value provides evidence. The null hypothesis is false. So it's the probability of our result occurring given the null is true. So what we're saying right here, and think about this. So answer this question. If I am a 6-minute mile runner, like let's say it's true that Brian's a 6-minute mile runner. Like let's just say that's true. What percent of the time would I run a 6-minute mile or longer? So think about that one right there, Jackson. If I am a 6-minute mile runner, then what percent of the time would Brian run a 6-minute mile or longer? So don't even worry about the data on the screen. But if I am a 6-minute mile runner, what percent of the time would you see me run a 6-minute mile or longer? If I am a 6-minute mile runner, what percent of the time would you see me over there run a 6-minute or longer? If I am a 6-minute mile runner. and you just go out and watch me run miles. If it's true that I'm a 6-minute mile runner, what percent of the time would you see me run a 6-minute mile or longer? Like, if that is true, you would see me run a 6-minute mile or longer, what percent of the time? And I'll start drawing it out to maybe help out. Not one, or longer, like takes me longer to run it. So you're kind of on the right track. I see where you're going with that. Well, not 100% though. 6-minute mile or longer. If I am a 6-minute mile runner, then a time of 6 minutes or longer should occur about what percent of the time? So given Brian is a 6-minute mile runner, does that make sense when I draw it like that? Then in observation, so this is the observed right here, you would observe me run something at 6 minutes or longer, what percent of the time? If Brian is a 6-minute mile runner, yeah, and does that make sense? Like, just viewing it right there to be like, well, if Brian, I keep erasing myself, if Brian is a 6-minute mile runner, then you would observe me run something at a 6-minute mile or longer 50% of the time. So think about this. Now let's go back to the problem we had here. If Brian is a 6-minute mile runner, then you would observe me running my miles in 6.2 minutes or longer about 7.8% of the time. So this is kind of likely, like, it's still theoretically possible, but let's increase this. We're just going to double this mathematically right here. So if you notice, I'm just taking the difference and doubling it. So what would the t statistic now be since I doubled the difference? So think I just doubled the difference. So what would the t statistic be? All I did was double the difference. So by doubling the difference, the t statistic would now be what? Because I doubled the difference. So this was 6.2, and then I doubled it to 6. It'd be 3 exactly. And you can work the math to double check it, but the t is now 3. So this 6.4 should be what, theoretically speaking? That 6.4 observation is going to be even more what, given Brian is a 6-minute mile runner. So now we're over here at the observation of 6.4, which is a t. If we do standardized differences, it's a t of 3 on the curve. So now that is an even what more result by random chance. Like, seeing Brian, it is statistically significant now, and it is less likely, right? Because now if we go and calculate the probability of this, you can say, well, Brian landed over here at a t of 3, and basically this is very unlikely by random chance. So at this point, I'm taking 6 minutes and 24 seconds to do my miles, and I'm like, I'm a 6-minute mile runner, and you're like, statistically speaking, there's evidence that you're slower than 6 minutes. Like, the observed results you're showing me, what I'm watching you do, is evidence that you're null. What you're telling me is not true. It's unlikely you would take this long or longer, a result as extreme or greater than. Does that make sense, Jackson? So the idea right here is, again, the probability of Brian running a 6.4 minute mile, given he is a 6-minute mile runner, is very unlikely, i.e. the p-value, which means we have evidence against the null. We have reason to believe that Brian's time is actually greater than 6 minutes because what we're seeing is unlikely given the null is true. So it always goes by the assumption the null is true, and it talks about the probability of your observed results given the null is true or a result more extreme. Really good understanding of what a p-value is right there. And yeah, these questions are pretty good. There's a few I'm kind of don't love as much. P-value of 0.01 means we should definitely reject the null. Pretty much. It really depends on what, which I think it's this answer right here. You reject the null when what? Very clear and easy statement. We reject the null when, here, I'll start writing it. Always reject the null when what? Which is assumed to be 0.05 unless otherwise stated. So usually we say reject the null when the p-value is lower than 0.05, but 0.05 is the assumed what? Which this question goes to. So when the p-value is less than what? Alpha. Yep. Great, Jackson. Let me throw 8,000 points, Jackson. Excellent work here in practice. These are the things to understand beyond just getting the questions right. So hopefully we're understanding the problems a little bit more in depth. False. Wonder whether the p-value provides evidence for the null. No, we don't do evidence for the null. This p-value provides evidence for the null. Wait, what? Whether a p-value provides evidence for the null. See, this is the problem. See, they do little tricks right here. This p-value provides evidence for the null. That's just false. We don't provide evidence for the null. This p-value proves. We don't prove. So we don't prove. We don't provide evidence for the null. So I hate to say it. I'm a little worried between these two. Whether a p-value provides evidence for the null, but we don't provide evidence for the null. We provide evidence for the alternative. That's a little bit mean. Oh, no. I was reading the wrong question. A p-value of 0.01 is evidence against the null hypothesis. True. I was reading D, and I was like, these are just wrong statements. I was like, it can't be any of these. This is true. If p-value of 0.01 is evidence against the null, well, then if it's sufficient evidence, depends on the alpha level, which we were mentioning. So just by knowing what we can and cannot say, we don't provide evidence for the null, so it had to be false. We don't prove the null, and we don't provide evidence for the null. We provide evidence for the alternative. So we were able to get it right without even knowing the question. Choose the correct answer below. Whether a p-value provides enough evidence to reject the null hypothesis, and that is a correct phrasing right there, and that's what we're getting at. We reject the null when the p-value is below alpha. So there we go. Let's see right here. I really like these questions. Let's see. So with this right here, using an alpha level of 0.05, the alpha level is when you reject the null. A p-value of 0.02 results in rejecting the null hypothesis. 100%. Statement is true. When the p-value is low, reject the null. P-value lower than alpha, reject the null. The alpha level depends on the sample size. How do we figure out alpha level? Which I think you know this one pretty well now, Jackson, because I think we've brought this up. Alpha level is just what? Alpha level, I'll show you how to do alpha level. Here's how to do alpha level. I want to use 0.10. False. It's just, you just pick it. Yeah, you just say, I want to use this alpha level. Alpha level is your type 1 error rate. Important thing to know right there. And so the researcher picks it. It's totally independent. The alpha level is independent. It does not depend on sample size, just based on, well, kind of, and so that is the associated alpha level. Good answers right there. It does, each confidence interval has an associated alpha level, which we see in the jump output. It does specify right here in a lot of output that 1 minus alpha level, the associated confidence interval coming to the same conclusion as a 95%. So the alpha level would be 0.05 if you were to turn those into tests. So it can be associated with the test, and it's basically based on the researcher, whatever they want to do. If you go over here and say, I want to make 98% confidence intervals, well, now I'm testing probabilities. Didn't mean to do that. There we go. If you say I want to make 98% confidence intervals, it's fun to click buttons. 99, why not 99? And now we are using a 0.01 alpha on the two-tailed test. With an alpha level of 0.01, a p-value of 0.08 results in rejecting the null. What should you do at this point? If your p-value is 0.08, what should you do with an alpha level of 0.01? So don't worry about their answers. Just think about what you should do. If you get a p-value of 0.08 and your alpha is 0.01, so your p-value is up here, your alpha is right here. So with a p-value of 0.08 and an alpha of 0.01, what should you do? You should fail to reject. So when the p-value is high, you fail to reject. This is false because only a p-value less than alpha results in rejecting the null. That is correct. Using an alpha level of 0.05, a p-value of 0.06 means the null is true. Do we ever say the null is true? No. We don't know whether the null is true or false. We only reject the null or we don't reject the null, which is fail to reject. This statement is false because a p-value greater than alpha only indicates there's not enough evidence to reject the null. These are excellent sayings right here. We do not have sufficient evidence to reject the null. It is better to use an alpha level of 0.05 than an alpha level of 0.01. Good work. Nice job, Jackson. And so a researcher using an alpha level of 0.01 would make what? The answer is it's researcher's opinion. An alpha level of 0.01 means the researcher would make less what? Very important. If you know this, then you really understand what alpha level is and what it controls. Kind of, but which errors? So if they went to an alpha level of 0.01, they would make more what errors? Pull up, we got a graphic for this somewhere. If they went to an alpha level of 0.01, they would make what errors? Almost to it. There it is. So more type 1. So if you change from an alpha, your alpha goes from 0.05 to 0.01, you would make more what or less what? Which ones though? You might have it. You might have it. Sorry, I'm like. So if you go from 0.05 to 0.01, you would do what? Perfect, Jackson. Perfect. Yep. Let me throw the 1,000 points. Perfect answer. Alpha literally is your type 1. So here I'll draw it out the way it's kind of worded in this. is if you go and decrease your alpha, which is type 1 error rate, you will increase type 2 and decrease power. So these are the ones that are positively correlated, and and that's negatively correlated. So that's exactly it right there. Good to see you, Kiddist, right here. We're talking about type 1, type 2 error, and those are the three things that control it. So is it better to use one of those? Well, depends on the types of errors you want to make. So the alpha level should be set. No. An alpha level, lower alpha lowers the probability of type 1, but increases type 2. Literally what we're reviewing right there. So if you know that and can explain that, you're good to go. It is better. Good job right there. Get all those points. It is, if we use an alpha level 0.01, then a p-value of 0.0001 is statistically significant. Once again, the concept of p-value less than alpha is statistically significant. So if you have a p-value of this, and you use an alpha level of this, yes, that is statistically significant right there. So most definitely. Very true. Don't even read their answers. If we use an alpha level of 0.01, then we reject the null hypothesis if the p-value is, well, yeah, right? If we use an alpha level of 0.01, then we reject the null hypothesis if the p-value is this. Yeah, I mean, you reject the null when the p-value is lower than alpha. That's exactly right. If the p-value is 0.01, we reject the null hypothesis for any alpha level. Wait. Oh my gosh. See, now they're reversing it. They're saying, here's your p-value, and you have an alpha level greater than this. So although I don't love the way that's worded, they're saying your p-value, they're saying the alpha level is greater than p-value. So they're saying if your alpha level is greater than your p-value, you reject the null. It's like, yeah. Yeah, so if alpha level is greater than p-value, you reject the null, which is not the way I word it. They're just seeing if you really know these concepts. Just once again, sometimes they word it in a tricky way. What is the name at the threshold? We reject the null. Once again, have this memorized. These are great things to put on flashcards. Effect size is the true difference between the null and the hypothesized amount. Yep, alpha level for this one. So if Brian claims he can lift 400 pounds, but he can only lift 398, that's a small effect size. Do you think you might believe Brian? Like if I say I can lift 400 pounds and I go to the gym and you see me benching 398 and I just do one rep on 398, you might be like, you know what? I kind of believe Brian. That's a small effect size, right? Because maybe you saw the truth. Like, how do you know you're seeing the truth right there? You might say, well, maybe he actually can bench 400 because I saw him do something very close to it. But if you see me struggling with like 140 or something, or 135, 245s on each side, so you see me struggling with that, weights are just falling off because I didn't put the clamps on. Put your clamps on. Then you'd be like, you know what? I think there's a big effect right here. Brian is nowhere close to 400 pounds. So my estimate of the effect size is evidence to reject the null hypothesis, and we could run p-values and all that stuff. Type 1 error is rejecting when the null is true and we reject it. Critical values are the point at which we reject, which can be calculated. I don't use them much. Alpha level is the point at which we reject. The p-value is smaller than the level of significance. What do we conclude? P-value is low, reject the null. And so we reject. We do not say this bad except word. We don't say the null is true. We don't accept it. We just reject or fail to reject the null. What is the probability that a test correctly rejects a false null hypothesis? So when you think about this, we can narrow down some things right here. Significance level is alpha. Great job, Jesse, right there. It's power. So a powerful test. And this is the textbook definition. The textbook definition of power is the ability to correctly reject the false null. But I want you to think about what power is and what it means to us. If we think about power right here, which is 1 minus beta, that's the formula for it. Power gets stronger if you have a larger sample size. We'll reverse time right here so we can see the arrows going up. What increases power? So think about this. When would it be easier to see Brian cannot bench 400 pounds? If you watch Brian at the gym 1 time or you watch Brian at the gym 10 times, when would it be easier to say, I have good reason to believe that Brian cannot bench 400 pounds? So when would it be easier to reject the null hypothesis that Brian can bench 400 pounds? You watch him at the gym 1 time or 10 times? When would it be easier to reject the false null? So Brian says, I can do an average bench of 400 when I'm maxing. My average bench is 400. You say, I am trying to show evidence that your average bench is less than 400. So when would it be easier to reject? When you watch Brian bench 1 time or 10 times? So you go to the gym and you watch me, see, you're like, okay, Brian's maxing. I'm going to watch him. So when would it be easier to reject the false null? Like, let's say my max bench is only 390. So if you watched me do 390 one time as a max, you'd be like, I don't know. You actually couldn't run the statistical test because you don't have a standard deviation yet. But I think in our minds, we'd be like, I think Brian maybe could do a 400 max. Like he did 390. So I don't know. That seems believable. His claim seems believable with what I observed. But if you were to go and let's change it to 100. So think about this. You've been watching Brian for 100 days and Brian's average max is 390. So now your test has a greater ability to reject the false null. Like, let's say Brian can't bench 400. I'm exaggerating right here. You will have a better ability to reject the null with observing me 100 times, i.e., the test is more powerful. So the definition of power is the ability to correctly reject the false null. And if the null is false, well, increasing the sample size will give us more ability to reject it. And so I like to say power is the ability to find results when results exist. So if it's true Brian can't bench 400 pounds, then observing Brian more will increase our ability to find out this truth. Now, what if Brian can only bench 90 pounds? Nothing wrong with benching 90, but if Brian can only bench 90 pounds, you probably wouldn't need to observe Brian benching 100 times. You might only need to observe Brian benching like 2 times. Very small sample size here. You'd be like, well, he claims 400 pounds, but I saw him only benching at 90 max. Nothing wrong with that, but Brian's not telling the truth right here. And I've changed the what now, Jackson, because Brian claims 400, but it looks like, as far as we can tell, the truth is closer to 90. So this difference you see right here is an estimate of the what, because we don't know what it truly is, but we have an estimate now of the what. That is an estimate. So for example, yes, let me double think of that. Oh, no. There wouldn't be a greater chance of type 1 error. Type 1 error is simply governed by the what. There'd be, if the sample size was smaller, there'd be a greater chance of a type 2 error. So if the sample size is smaller, so think about if you decrease sample size, to Jackson's question, and you are correct, Jackson. Yep, and then you got the next part, right? So if you decrease sample size, you will increase type 2 error and decrease power. A test with a smaller sample has less power and has more type 2 error. So you'd be more likely to fail to reject the false null. And think about this. If we go back in time right here, you'd be more likely, like let's say Brian can't bench 400 pounds. You'd be more likely to believe me if you only watch me what? So Brian can't bench 400 pounds, but you'd be more likely to believe me and make an error if you only watch me what? Which is a type 2 error. Because the truth is the null is false. Brian can't do this. The null is false. But you'd be more likely to make the type 2 error and believe me, fail to reject the false null if what? Going right here with this. You'd be more likely to believe me if what? And Jackson, I'll say that next here. If the sample size was smaller, right? So with smaller sample size, now sample size does not impact type 1 error. Now there are calculations we can do where we can try to like set things to certain values, but type 1 error is just alpha level. I'm saying if you could bench 400 pounds, wouldn't we commit a type 1 error if we only saw you bench 390? Well, you could. So a type 1 error is when the null is true and we reject it. But think about this. If you see me bench 390 could be a what amount? Like, let's say we ran the statistics and the result came out over here. Now, 400 is what you expect to see. And 390 is right here when you run the result. So we're saying that 390 is what we saw. That is a what result now? A somewhat what result? So you saw me bench 390 like 10 times. So you saw me bench 390 10 times. We ran the analytics on it and we got the following. So 390 is a what result? Insignificant, right? So you'd be like, you'd believe me, right? because I bench something you would expect by random chance, given I can bench 400. Like the result of 390 is a likely result by random chance, given I can bench 400. So this is where the alpha level comes into play. And the alpha level is going to be down here, about over here. So the alpha level says, here are the observations that would only occur 5% of the time. So this is your willingness to make a mistake, because are all of these results right here possible, given I can bench 400? Are all those results that I've circled possible, given I can bench 400? Good job, Jackson, right here, really understanding this. Are all those results down there on the lower end possible? They are possible, but they're unlikely, right? So when you set your alpha level, you're saying, what is kind of unlikely enough? Like maybe, result of this is unlikely enough, but it's a little bit subjective because it's possible that you could make an error. Like maybe I just have an off day or two and I land up over here and you reject the null and you're like, I reject the null. You can't bench on average 400. And I'm like, I just had some off days. Those were some of the lower days you saw. You just, I was not truly maxing. So it's possible you could make a mistake because all of these results are technically possible, i.e. likely by random chance. But what is unlikely enough, that's defined by the alpha level. So does that, I feel like, Jackson, you have a much better understanding of these concepts right here on what type 1, type 2 error is. And type 1 error is just totally independently set, but it does impact type 2. So if you lower your alpha, you will increase your type 2 error rate. You'd be more willing to believe Brian. So that's what type 1 error is controlling right here. Like you say, I need a lot of evidence. Like I would need to see Brian only bench 100 pounds. And that would be probably, you're setting kind of a critical value at that point. Also estimating the effect size. I don't know. It's a lot of concepts here which come to play. So I like doing examples like this. Yeah, so we'll finish this up right here. The probability we correctly reject the false null is the power of a test, 1 minus beta. There it is right there. What is the name of the difference between the null and the truth? So when Brian can only bench 100 pounds, but he claims 400, that is called the what, or an estimate of the what. So the difference between the null and the truth, critical value is the point at which we reject. Alpha level significance, effect size is the difference between the null and truth. Type 1 error is rejecting the null when the null is true. Here we go, the bank scenario. I guess we'll end with these. What type of error is made when the true null is rejected? In a type 1, the null is true and we reject it. In a type 2, the null is false and we fail to reject it. I'm going to go over here. So maybe I do these things quickly sometimes, but if this is your first time seeing me do these, write this down. In a type 1, the null is true. That's a T and we reject it. In a type 2, the null is false and we fail to reject it. The 2 F's of the type 2. So what type of error is made when the null is true and we reject it? It's a type 1 error. There we go. So here you go. Each of these situations right here mark type 1, type 2 error. That's going to help us with these. A bank wants to know if their enrollment on their website is above 30%. So that's the evidence we're looking for. Based on a small sample of customers, so very small sample size, the test has the null. The proportion of customers is equal to 30% versus the alternative. The proportion of customers is greater than 30% and rejected the null hypothesis. Later, they find out that it's actually 28% of all customers enrolled. Choose the correct answer below. Yeah, see you, Jackson. I'll finish these questions off right here and then respond to some emails. Now, what's interesting about this is they were looking for evidence. They were looking for evidence as what? They're looking for evidence that's greater than. So what should they have done? Well, they shouldn't have rejected the null. So they found evidence when evidence doesn't exist, because the null, it's very interesting because it is a type 1 error. Yes. The actual value is not greater than. So they found evidence for something that is not true. The null, what they saw in their data is where I get a little, because it's not like the null is true, but they did make a type 1 error where they found evidence for something, because usually we don't know the truth. They should say but the null is true. So there we go. Don't like how that goes. So once again, a type 1 error is when we reject the null and the null is true. So the actual value is not greater than, because they said they have evidence that it's greater than. So that would be wrong right there. A student tests 100 students to determine whether other students on our campus prefer soda brand A versus soda brand B. They find no evidence that a preference for brand A is not 50%. A marketing company tests all students on campus and finds no difference. This is much better because what the student found is that it's 50%, and the marketing company found 50% also by testing all students, which means they know the truth. So right here, there is no error made. The actual value is 50%, and they did not reject the null. So that's really great. Exactly, no error. They found the correct conclusion, which really, I hate to say this, these questions are a little bit theoretically weird because usually you never know the truth. And you're telling me a marketing company came and found exactly 50-50? Like, it's highly unlikely if you tested all 30,000 students at UT or whatever that you'd find exactly 50-50. So, bit odd. A human resource analyst wants to know if the applicants this year on average, what are the chances of that? Very unlikely. Well, we could calculate it if the truth is 50-50, right? Oh my gosh, Jesse, do you want to know the chances? Here, watch this. You ready to finish? This is kind of the cool stuff. So if, here's what we can do. We can actually calculate the probabilities. We have to go over here to binomial distribution. So if, this is going to be the easiest way to calculate it. I'm going to go here to binomial, and we're going to figure out the probability. Okay. Binomial applet calculator. Okay. So if there are 30,000 students at UT, and we have 50 right there, is it going to draw it for me? Oof, look at it crashing right there. So it's having a hard time with this. Let's see if it gives a probability out. It's probably going to be so small we can't even calculate it. We want to find out the probability of exactly 50%. So that's going to be this. Is going to calculate it. I might need to use R to do this. It's saying it can't do it. It's all kinds of mad at it. But so now we got to go over to R, and it's binomial. I think we want the PDF, right? Binomial PDF in R. Here we go. Here we go. We want to use the following and prob. We don't want prob. Size equals this. Prob equals this. Oh, yeah, good. Probability 50% is true. Size, and let's go to 6. There's that. 6, 12, 50%. Let's see if that's what I should be getting. So 12, observation 6. Good. Okay. So there it is right there, showing exactly 50% with 12 students. But now we want to go to a much larger number. So we have to go over here and go to size, 30,000 students, and seeing exactly half, which is that. And the probability, no way, really? Huh. What is the most likely result? Well, it's not as unlikely as we thought, Jesse. The probability is about 1 in 220 or so. It's about 1 in 220. Wait. What? Divided by 1. No, 1 divided by. Yeah, 1 in 220. So a little more likely than we thought. And basically, the applet can't carry out that many digits, but it's doing the same sort of thing as the applet right here, finding the probability of that one occurrence. But it is the most likely. If you look at these curves, the center of the curve is going to be the highest peak. And we could see something with like 1,000 observations and 500. Oh, it can't even do that. Come on, your applet's bumming me out, man. It's just too much for the applet to handle. Wow. 300? Starts to break at 200, I guess, right? There we go. And there is the probability of observing exactly 100 with 200 occurrences. And we could do the mathematics on that with permutations, but using software is much quicker to solve. So yeah, well, I guess if 50% is true, it would occur about that percent of the time for a UT population, about 1 in 212, 220 times or so. A human resource analyst wants to know if the applications this year on average higher on their placement exam than the 552.5 points the candidates averaged last year. She samples 50 recent tests, and the average type 2 was type 2. Oh my gosh, Jesse, great job. And finds the average to be this. She fails to reject the null, so that is open to a type 2. That the mean is this. At the end of the year, the candidates this year had a mean of this, so it was higher. So she failed to reject the false null. So this is a type 2. The actual value is this, which is greater than. So she failed to reject the false null. Jesse, another 1,000 points. Keep up those answers. Great job right there practicing the questions, because that's what we want to be able to do. A pharmaceutical company tests whether a drug lifts the headache relief rate from 25% achieved by the placebo, which is just a sugar pill, basically. They failed to reject the null, so this could be a type 2. because if you fail to reject the false null, it's type 2. With a p-value of this, good deal. Further testing shows that the drug actually relieves 38% of people's headaches. So once again, this is the same thing right here. The company made a type 2 error. The null hypothesis was not rejected, but it's false. The true headache relief is greater than. So that is a type 2. These are pretty good. Only one of those did I dislike. Yep. And so only the one where it was like, it should say what error does it look like they've made, or the company should believe they made a what. Like maybe they do a small pilot study with like 20 people. Then they do a study with like 300. So it looks like the company, you know, when they did the first test, made a type 2 error. So a lot of times people do what's called power analysis if you're working for manufacturing companies or doing research to figure out the sample size needed. So pretty good questions. We always like to critique things and be like, how could it be better? But great work. Type 1 error rate. Oh yeah, yep. What type of error is made when a true null is rejected? Type 1 error. Jesse, I feel like I am excited for this test. I feel like, do you notice how a lot of these topics converge? Like, here is the last chapter, Jesse. Are you ready for it? The last chapter is the following. We are going to run analyze fit y by x, and let's see right here. You know what you can do? Let's say if people have a high or low GPA, I'm going to create a new variable. It's too much work on that one. Where's the data sets I have? I could do it in R really quickly. It's that these are going to come out kind of boring. So let me pull up a data set that actually has something worth analyzing. And I think this one might. Okay, good. This one does. So here's the last chapter. The last chapter right here is 2 categorical variables. So that's a condition that we have 2 categorical variables known as count data. So get ready for that condition. Let's see if gender can explain if someone has broken a bone. So you ready for the null hypothesis, Jesse? For this chapter, we do not use notation. The null hypothesis is gender is independent of breaking a bone. So what do you think would be the alternative? The null hypothesis is gender is independent of breaking a bone. I'll say, like, whenever you see this chi-squared stuff right here, just remember the null is gender is independent of breaking a bone. So what do you think the alternative would be? So the null is gender is independent of breaking a bone. Like, gender would tell you nothing about someone breaking a bone. That's what independent means. It's like, if I know someone's gender, would give me no information. You can say dependent. I like to say not independent, but dependent works also. Great job. So you can say gender is dependent on breaking a bone, or breaking a bone would depend on someone's gender. And so think about this. Here's the p-value, and you'll hear me say in class, the Pearson test has the p-value. So the Pearson test right here has the p-value. That's the chi-squared test statistic, like a T or Z, but the p-value is right there. So what are you going to do to your null hypothesis? What are you going to do to the null hypothesis? You're going to do what to the null hypothesis here? What are you going to do to the null? I mean, because there's the p-value, right? The p-value is 0.00001, because remember, p-values are probabilities. We'll show in class how to calculate the chi-squared test statistic. You're going to reject the null, right? So, I mean, think about how you'd write this up. My initial belief is that gender is independent of breaking a bone. I now have what? That gender is what? Because my p-value of 0.001 is less than my alpha, I'm going to reject that gender and breaking a bone are independent. I have what? And then you could also comment this. I have evidence that they are dependent, right? And it looks to me that males are more likely to break bones than females. It doesn't mean males break bones. It just means they're more likely, and there seems to be an association between someone's gender and the probability of them breaking a bone. So that's like a 5-minute summary of the whole chapter. And that's an estimate of the effect size right there, the difference between the 2 distributions, which is the conditional distributions to go back to an earlier chapter. What about this, though? If we go here and look at somebody, let's go to breaking a bone. And does that explain if somebody has smoked weed? Yes! I love it! Because Jesse, wow, look at this. I picked good variables. Look at that. We could have done great. Yeah. So just tell me, I don't know if you saw it, but look at that difference. That difference, which is very hard to see. There is a difference, I believe. That difference looks super duper what? That difference between these 56% up here, we'll go to the bottom ones, 44%. Come on, trying to go there we go. This 44% right here and this 43.85, wow. That difference is very, very what? That difference is very, very what? That difference between these, they're so close, right? So it's a very small difference. And a small difference would be what? A small difference would be what by what? The small differences we see right here would probably be what by what, which is the difference in the conditional distributions. High p-value, i.e., these differences we see are likely by random chance. If someone's like, well, I do see people who have broken a bone are a little bit less likely to have smoked weed. And you're like, this is a difference of like one person basically between like hundreds of people. Like there's like one extra person in one of the groups basically that's kind of pushing it to a higher percentage. It seems to me these differences are just super likely by random chance. And think about this, the p-value would be 1 if the bars were perfectly what? The p-value here would be 1 if the bars were perfectly what? So that is the most likely thing by random chance. The p-value would be 1 if the bars were perfectly what? And that's when you get a p-value of 1 on this. If the bars are perfectly what? Perfectly even, right? Because if there is no difference, we would, like, if the variables do not impact each other, then the most likely thing to see is that they're perfectly even. But when you go to things that are kind of more of a relationship right here, like let's say your views on legalizing weed, do you think that impacts smoking weed? Or let's say, does smoking weed explain if someone wants to legalize weed? So we're asking, do we think the null would be someone smoking weed is independent of their views on legalizing weed? I mean, I think if people smoke weed, they might be more likely to want it legalized. Notice here how the distributions look very different. The conditional, like if someone smoked weed or if someone has not. So the p-value here is going to be super duper low again. If you hover over it, you can actually see it. You have to kind of do a little trick on it, right? You going to do it today? You going to show the p-value? You want to show? There it is. It's got about 29, 30 zeros on it. So it's a super duper small p-value right there because these differences are super unlikely by random chance. You do get some weirdness though, like someone who's smoked weed or 6 people who have smoked weed and said completely illegal. And then you've got over here people who haven't, and they want, a lot of them want it to be recreational usage. And this is an older survey, so not trying to do any social political views, but it's interesting to see. And I wish we had asked this question every year to see changes in the distribution over time, because then we could look at that and actually do an analysis to see if over time is it changing and do a time series on this data. So that's would be pretty interesting because this data is about a decade old. And still, if you look at the marginal distribution over here, which is all students, 56% of all students, over half of students who are now in their 30s, over half of individuals say, yes, just make it legal for recreational usage. The percent that want it completely illegal, which I think it still is 6.45%. And those are the marginal distributions. But think about this. Someone's views on legalization weed looks highly what on if they've smoked weed. So someone's views on legalizing weed looks to be highly what if they've smoked weed, which is what the p-value tells us right here. There's evidence of that. Evidence to the alternative that someone dependent, right? So that's the chi-square test of independence. And it's easy to remember the null because it's the chi-square test of independence. The null hypothesis is that the two things are independent. I like this chapter a lot, Jesse. I consider it to be an easier chapter. There's going to be some math parts of it where we find out the expected counts and the cell chi-squareds. JUMP can do all this work for us down here where we can just solve for the values. But we have to know how these values are found, and you'll see me do these during class, and my Pearson will actually do a decent job. I like to make fun of my Pearson, but it'll have you do a decent job of finding the cell chi-squareds and the expecteds for the cells. And then we'll talk about what an expected means. It actually goes back to probability. But yeah, it's kind of the whole chapter. And think about this. You now know how to analyze categorical data. The only thing we haven't done is we have not done a categorical Y and a quantitative X. That's the only combo we haven't done. So because we did categorical right there, we did quantitative, and then we've done categorical down in the X and quantitative in the Y, which is going to be difference in means right there. So that's difference in means. That's a categorical X, quantitative Y. Then we've also done quantitative, which is regression or correlation, QQ straight enough, no outliers. There's 2 quantitative variables. We can just fit a line to that. And then we just did a moment ago 2 categorical variables. Let me hover over those and I'll show you the last thing. Okay, so going in order from right to left, we have on the screen right now two categorical variables, two quantitative variables, and a categorical x, quantitative y. So the only thing not on the screen is a categorical y and a quantitative x, and that gives you what's called logistic regression. So this is logistic, and I wish here we'll show it. There's, oh, really? You got to show the sigmoidal S-shaped curve. Okay, we'll do a stronger relationship. It actually runs the logistic and shows you the curve right away. So let's go here and go to student loans explained by high school GPA. Should be sigmoidal down. It is. My only qualm is you really can't see the S shape to the curve because it looks like a line. And I'm trying to find one that's strong enough you can really see the strong S shape. What is even stronger? Well, let me cheat. Fit model. And let's go here to predict someone's gender. And let's go crazy. Should do it. Nominal logistic. Cool. Level of interest. Cool. And let's run it and see the sigmoidal curve. Oh, it doesn't show me the sigmoidal curve? Come on. Yeah, this is a horrible idea. Some statistician is going crazy. Can I do the profiler? Oh my gosh. This is Brian just having fun at the end of office hours. Look at all, oh, major. I should not have included major. Acts like an indicator. Okay, last try. Last try. Well, I can do it over here in R. Here, let's show the sigmoidal curve. Sigmoidal curve is going to be MGLM. Predict someone's gender based on their height. Data equals survey 10. Not surf. Survey 10. And family equals binomial. And now visualize model. And we get to see the sigmoidal S shape. That's one thing I was just unhappy with as we were plotting this out, because it's not a line, it's an S-shaped curve. It's just the stronger the relationship, the more the S shape. So if we use high school GPA to predict someone's gender, you can kind of see a little bit of the S shape right there. But if you extend out, which I wish they extended it further, you'd be better able to see. It's not a line, though. That's an S-shaped sigmoidal curve predicting the probability of somebody being male or female based on their high school GPA. And the probability of male is the points below, or, well, the area below here, which at a higher GPA, we see a lower probability. I think we have the same data. Do we? Is this the same data? GPA? It looks to be the same data. Let's take a look. I think so. I think it's the same data if we go to 4.0 right here. It's just that this one extended it out a little. Yeah, there it is, same curve. And if we go to 0, well, it doesn't show it on this graphic. But if you notice, it kind of flattens out as you go over, and you can see the S-shaped curve, but easier when it's a stronger relationship, i.e. more statistically significant. But if you do something like, what is a variable that's not going to show us really much of anything? Glimpse. Do I have glimpse on? Good. Something like cell phone contacts, probably not a strong relationship, so it's going to be a more flat model. And that's what you see right there when the relationship in the model is not statistically significant, a much flatter model. And these are concepts, so if you've watched, I've gone a little bit over time right here. Started a little bit late, so it's fine. But these are concepts we cover in 320, and we understand what the sigmoidal curve is, the idea of statistical significance, and we apply these ideas, and we make predictions, and we work models. But that's got it. We'll be back next time. Thank you so much, everybody. Little advanced view right there, kind of reviewing the topics. Until later. Bye for now. Bye.